To get ourselves started, let's do a review. Look at the function f of x comma y equals x cosine of y minus y times e to the x, and find the gradient of this function at the point 1 comma pi over 3. So first, we should find the two partial derivatives. So partial with respect to x should be cosine of y minus y e to the x, and the partial with respect to y will be negative x. We just really copy x first, right? And then differentiate cosine of y to be negative sine of y. And then minus, since we're differentiating with respect to y, x is a constant, therefore e to the x is a constant. So we copy the constant, and then, well, constant times y just would differentiate to the constant. So we stick those two things together in a new vector to create the gradient. And then we just need to evaluate this at 1 comma pi over 3. So replace all the x's with 1s and all the y's with pi over 3s. We get a thing that looks like that, which will clean up this way, right? Cosine of pi over 3 should be 1/2, and sine of pi over 3 is root 3 over 2. And if we just clean this a little more, I guess this is as nice as it will look. So the vector that we get, and it is a vector, right, is 1/2 minus pi over 3 times e, comma, negative root 3 over 2 minus e. Now, we'll reuse this a little bit later today. Okay, from Calc 1, I'd like to recall this idea. It might be a little obscure of an idea, but it's actually a very useful one. Given a function y equals f of x and a specific x value called a, well, you take the derivative, right? And so the derivative is supposed to be the slope of this red line, this tangent line. And, there's an app here that will show you what that tangent line looks like. Here you go, right? So I just have some function in here by default. You could certainly put in a different function, and you can take the point wherever and, move this along to see, this line. And the key thing is that the tangent line, well, has slope f prime of a. I mean, that's why f prime had that limit-based definition the way it was. It was meant to capture the slope of the tangent line. And okay, so yeah, the tangent line has slope f prime of a and goes to the point a comma f of a. And so you've got the slope and you have a point, and you can, from that, create the equation of a line in point slope form, right? So y minus the y value f of a equals the slope, which is f prime of a, times the quantity x minus the x value a. And if you just solve for y in this, you just need to add f of a to both sides. So y equals f of a plus f prime of a times quantity x minus a. The point is, there's this thing called linearization, which is really a function whose graph is the tangent line. Okay, so this line in red, it should be the graph of some function. I mean, just like the blue is f of x, and that's the graph of a function. This red line itself is also the graph of a function. That's the linearization. And so since we solved for y, I just really copied what's in the yellow highlight there. That's L of x, right? So the linearization of a function is really just creating the equation for the tangent line, but needing to solve for y, and we'll call that the linearization. So there's an approximation here that's going on that's really awesome. If you have an x value that's near a, maybe it's not exactly a, but somewhere nearby there's an x value near a, then the linearization, the y value of the linearization and the y value of the original function should be near each other. So take a look, right? When you're nearby, the red graph and the blue graph are very similar to each other, right? And the point is that the linearization is easier to compute than f of x, at least in a general sense, right? So your function f of x might be very wacky, but L of x, that's a line. Y equals mx plus b is very easy to deal with. Okay, interactive question. For linearization, why does x have to be near a? Or rather, to flip it around, what goes wrong, or what can potentially go wrong if x is not near a? In Calc 3, given a function f of x comma y, so with two input variables and a specific input a comma b, this is what the equation of a tangent plane looks like. So it uses partial derivatives. I mean, this looks a lot like point slope form, but it had to be modified. We're not going to go through the details. You just have to trust here that you do z minus an actual z coordinate here, which is f of a comma b, and then we have the partial with respect to x. That's the thing that plays like a slope times quantity x minus the x value a, plus a thingy that operates a lot like slope, so that's the partial derivative with respect to y, times the quantity y minus b, where b again is actually a specific y value, right? So I want you to see the two terms on the right side of this equation as very much like two copies of the type of thing that happens in point slope form. So then solving for z, all we have to do is add f of a comma b on both sides. And this, what you see in yellow, we've solved for z, so that's linearization, right? So that's the formula we're going to assign to this new function. So let's get this clear. There's an original function called lowercase f, and then if we just based on the equation of the tangent plane solve for z, we want to create the linearization as being a new function whose graph is the tangent plane. And an approximation thing happens, which is great again. So if you have a point x comma y that's near the point a comma b, then the linearization and the original function give you nearly the same output. And this is really nice because planes are much easier to compute with than just any old wacky function you could possibly get as f of x comma y, right? So yeah, the L of x comma y is easier to compute with, right? So let's just get a picture of what's going on in this interactive app, right? So you can actually type in any function you want for f of x comma y, move the red point a comma b in the left half. The default happens to be -4 comma -2, and then you'll see the tangent plane, which is based at that point a comma b in the right half. So let's click on this and see what happens. Okay, so here it is. You can type in your own function if you want at any point, but the default one in here is x squared divided by 10 plus y squared divided by 12. And the point is here, we're seeing the linearization, which is based at the point -4 comma -2, and you'll see in purple is the graph of the original function f, and then here's the tangent plane. So I mean, I hope by spinning this just right, maybe I'll just get this to free spin for a second. I hope you see that plane is just barely touching the graph at that point -4 comma -2, and that plane, if we want that to be the graph of a new function, and that new function is called the linearization. And then if I just instead look at the tangent plane that's not based at that point, how about a plane that touches this purple thing at a different location? So yeah, maybe like right there, right? And so then, right, this red point, sorry for, it's always hard to see exactly what's going on, but the red point, the one point shown in red, which is the common point of the plane and this purple region, has x coordinate 3.87 and y coordinate 1.62. And so let's just kind of move this around a little bit. We can see, the computer is just doing all the hard work really for us here. Actually, maybe I'll just comment. Sorry for if you actually zoom in on how this looks, you'll see like an x minus minus whatever, and I didn't bother making the computer simplify minus minus to a plus sign or whatever. I designed this as quick as I possibly could, and so all that actually I made the computer do is I actually made this computer program compute partial derivatives, and I just, instead of trying to get the computer to be really fancy about drawing the plane I didn't describe the plane here by saying it's tangent to the purple surface. What I did was I just literally, based on this linearization formula, I just fed this into GeoGebra, and then it created the appropriate plane. I mean, it hit where it needed to.